Okay, so let's start now with this example. So let's assume that we have A. This matrix is going to be like this: 1 minus 1 0, 0 1 1, and 0 0 minus 1. As in the previous example that we have had before in previous video, the characteristic polynomial is, as we have said before, characteristic polynomial of the matrix A in terms of the parameter lambda. It is going to be lambda. Okay, the identity matrix 3 means that it is the order of it, or the number of rows and number of columns, minus A equals 2. So we are going to put this determinant as it is. So it is going to be lambda minus 1, because this is 1 here, and then lambda after that for the remaining parts or remaining elements of this determinant. We can obtain it easily by multiplication of lambda and the element of I3. So if we have I3, it is 1 1 1, so we have 0 0 0 0 0 0 1, right? So these are this is I3. So in this case here we are going to multiply lambda by 1 and subtract 1 from it. So it is lambda minus 1, and so on and so forth for the remaining elements. I think it's easy for you to obtain. Then try to get the determinant of this equation, or of this matrix. You are going to find it. It is like this: lambda minus 1 to the power 2, take care of this, times lambda plus 1. Okay, then we want to obtain lambda, so we're going to equate it with 0, and then we're going to obtain the roots. So the roots for this equation, it is, as we said, lambda minus 1 squared times lambda plus 1. Okay, so this means that as if it equals to lambda minus 1 times lambda minus 1 again times lambda plus 1. So our roots are as if they are repeated. Do you remember we said that? Repeated. So here it is like 1 1 minus 1. They are repeated. These two are repeated. Okay, so this polynomial has roots 1 1 minus 1, and these are the eigenvalues of A. The root 1 has multiplicity, as we said, multiplicity 2 means that it is repeated 2 times, as we said, and must be listed twice as an eigenvalue of A, and we have mentioned about this before, right? Okay, A has 3 eigenvalues in this case. Okay, let's go to find an eigenvector associated with the eigenvalue 1. So we have 1 1 minus 1. Okay, so let's go with the first one here. So we are going to substitute in this equation with lambda equal to 1. Instead of lambda, we are going to put 1 here in this equation, this system, okay, with x here. Remember, because we are going to solve it as we have solved it before in the previous videos, right? So we are going to obtain the solution of this system. So we need to solve this system. When we solve it, so this is this part, which is 1 times the identity matrix minus A times x. So we're going to have, this is the new coefficient matrix times the vector of unknowns equals to the vector of zeros, right? Can we solve this? This system of 3 equations and 3 unknowns has the general solution. You can do this better than me, of course, because you are already trained on this. So we have the general solution of alpha 0 0. So any number that does not equal to 0, okay, real number that does not equal to 0, and this is an eigenvector associated with 1 for any alpha does not equal to 0. Okay, so that's the eigenvector that is associated with what exactly? The first lambda, the first eigenvalue. Okay, what about the others? Let's go and jump into the other. For eigenvectors associated with -1, okay, put lambda equal to -1 in 2 of the theorem. Okay, 2 of the theorem, which is, do you remember the theorem that we have? This is here. This is 2, as I have mentioned before, that remember this 2, because so we are going to put lambda here, we're going to put it -1 in our example. Okay. Okay. Then we are going to have our new coefficient matrix, which is going to be, as you can see here, -2, 1, 0, 0, -2, -1, and 3 zeros. Do you remember this? Okay. Anyway, so we have this system equal to the vector of 0. Then we need to get a general solution for it. So we're going to obtain the general solution of this system easily based on what we have explained before as this vector, beta 2 beta -4 beta. And this is an eigenvector associated with 1 for any beta does not equal to 0. Okay, so this is going to be our solution, or our eigenvector associated with the system that we are describing for for this A. Okay, now let's go to another example, or before that we're going to have a little theorem here, and then we're going to have another example. Suppose the n by n matrix A has n distinct eigenvalues. Take care of this word, distinct, different. Okay, then A has n linearly independent. Take care of this word. So if we have n distinct eigenvalues, then we're going to have n linearly independent eigenvectors. And this is very important. If our lambdas, okay, they are distinct, this means automatically that our eigenvectors, okay, our eigenvectors, they are going to be what? Exactly independent. That's very important. So the distinction of lambdas or the eigenvalues means that linear independency of our eigenvectors. Okay, remember that very well. Okay, now let's go and see this example that we are going to solve. Assume A equals to this matrix. The eigenvalues of A, we can obtain it, okay, as we have explained before, supposedly to be -3, 1, and 1. Okay, so you are here having 1 and 1, okay, with a repeated root of the characteristic polynomial corresponding to, let's start now with the first root, the first value of lambda. So corresponding to -3, we find an eigenvector. This is the eigenvector. You can check it also by yourself. Okay, this is the eigenvector. So -3 as lambda, it is corresponding to this vector, which is 1, 3, 1. Okay, okay. Now look for an eigenvector corresponding to 1, because we have 3 different values of the eigenvalues. We must solve this system, which is substituting with 1 instead of lambda in point 2 in our theory, and the system is going to be having x1, x2, and x3 as unknowns here, x1, x2, and x3, and this is our matrix, okay, our coefficient matrix, equal to vector of zeros. Okay, what we are going to find, okay, if we put them, we are going to find that this system has the general solution. Please check it also. It is going to have this general solution, alpha times 1, 0, -1 vector plus beta times 0, 1, 1, in which alpha and beta are any numbers. Okay, do you remember that we have solved many examples similar to these ones for our solutions, okay, for our systems? So we have general solutions similar to this, alpha and beta here. Now we can put, this is arbitrary, we can put any value, so we are going to like let one of them vanish and the other is going to be with 1. So we're going to assume that alpha equal to 1, beta equal to 0. Okay, and then we are going to put alpha equal to 0, beta equal to 1. Then we are going to obtain two linearly independent eigenvectors associated with eigenvalue 1. So we're going to have two different eigenvectors associated with 1. Okay, so that's the issue. Okay, so here we can say for this matrix we can produce three linearly independent eigenvectors, okay, even though the eigenvalues are not distinct. Okay, for this matrix this is what happened, which is a little bit not in the same context as we have mentioned in the theorem. Okay, but for this matrix we can produce three linearly independent eigenvectors, as we have said, even though the eigenvalues are not distinct. Okay. Okay, so anyway, so now I think that we have enough like knowledge now regarding the eigenvalues and eigenvectors, and I think that we can go to the home assignment after that. So this is the home assignment. Find the eigenvalues and of the matrix. For each eigenvalue, find an eigenvector. We have these two problems, so please solve them, and I hope that they are going to be easy for you to solve. Okay, thank you, and see you in the next video.